Over the summer in Chapter 2, you learned 4 basic kinematic equations, and we use those for one-dimensional motion. We can also use those for two-dimensional motion. So, quick review of them. Our first equation, we have change in position is equal to 1/2 initial velocity plus final velocity times change in time. Our second kinematic equation is final velocity equals acceleration times time plus initial velocity. Our third kinematic equation is change in position equals 1/2 acceleration times squared plus initial velocity times time. And our final kinematic equation in one of its versions is 2 times acceleration times change in position equals final velocity squared minus initial velocity squared. A reminder that if you don't have those equations memorized, you probably would do well to get them memorized because you're going to be using them a lot, and it's quicker to know them than to have to try and find them on the equation sheet. So let's take a look at vertical motion of a projectile first of all. Before we do that, let's back up and define a projectile. A projectile is simply an object that travels through the air. So looking at the motion of a vertical projectile, we're going to make some substitutions. If we're dropping something or if it's falling, many times we have an initial velocity of 0. And so when you're talking about a projectile and you get the single word drop, that gives you 2 pieces of information. First of all, it tells you the initial velocity is 0. And the assumption that we're going to make is that unless specified, we're going to be doing this stuff on Earth. And the acceleration due to gravity on Earth, we represent with the letter G for gravity. It's gravitational acceleration. It's not gravitational force. So gravitational acceleration is G. The value for that is 9.81 meters per second squared. So that single word drop, when you're reading it in a problem, gives you those 2 pieces of information. Delta Y, sometimes it's called dV for vertical displacement, or dy for displacement in the y direction, are also going to be terms that we will use. So in any of the problems, we can substitute a G in for an A if we're dealing with a vertical projectile, if it's not motorized or having something pushing it, if it's accelerating or decelerating because of free falling and gravity, then we can put the G in for the A. Okay, the horizontal motion of a projectile is a little bit different. Horizontal motion of a projectile is constant for velocity. This is really important. This is a really big idea. The reason for that is when we get to forces and talk about Newton's laws, Newton says that an object that's moving is going to keep doing its thing, keep moving in the same manner unless an outside force acts on it. Well, when something's flying through the air, the horizontal motion is only being influenced by the object traveling through air molecules. And for our purposes, air has no resistance. There may be some problems where air resistance is specified or you're asked to solve for air resistance. But if we're just talking about projectiles, something flying through the air, no air resistance, no friction. Therefore, there's no outside forces acting on our projectile. So in the direction it's traveling horizontally, its velocity is constant. So if we want to look at those kinematic equations that we saw earlier, for horizontal, change in position is equal to horizontal velocity times time, and that's a constant. Acceleration is 0 in the horizontal direction, and time is however long it's traveling. For vertical, the most common equation we're going to use is delta y, or dy, is 1/2 times gt squared plus the initial velocity in the y direction times t. So let's take a look at how this works. So here we have a projectile, and let's launch it at a 0 angle. So it's heading straight off, and let's make it go a little faster. Nice multiple. There we go. 60 meters per second, strictly horizontally. And what we're going to have it show us is a launch speed is listed up at the top, launch angle, and we'll be able to measure the time it's in the air and how far it's going. Range is horizontal change in position. So let's launch it and see what happens. Okay, each of the dots is some time interval. It's not a second because it says the time of flight is 6 seconds. But as you look, these red dots are horizontally evenly spaced. And that's easier to see because we have these vertical lines every other dot, and it's very easy to see they are very uniformly spaced. If we wanted to put in the horizontal lines, now we can see that as the object continues on its path, its vertical displacement increases. Why is that? Well, if we remember that horizontal velocity is constant, so my vertical lines showing that are going to be evenly spaced. When something's falling, however, it accelerates because the acceleration due to gravity is pulling it down faster and faster towards the surface of the Earth. So that means that each second of time it's traveling, it's going to speed up, and the distance vertically between the dots is going to increase. And we see that with this particular diagram. So we've got it at the same height. Let's put it at a little bit slower, and let's show both the vertical and the horizontal lines, and we'll be able to see how far it goes and how long it's in the air. They're uniformly spaced in the same manner as they were in the previous example. What we see now is that we have a much more obvious increase in the distance between our vertical positions because our object is accelerating. It's in the air for a longer time this time, but it doesn't get as far. That's because it's not going as quickly. Okay, so we've taken a look at two examples of what happens when I launch a projectile horizontally. So I'm standing at some surface above the ground, and I throw something out with some initial non-zero speed horizontally. Gravity's going to pull it down, so it's going to curve down and eventually land. Well, what happens if I don't launch it horizontally? If I launch it up at some angle, now what happens?